So, one last thing before we officially get ready for a AP test. We have one more topic to cover. And that's to do with what's called simple harmonic motion, or something that oscillates. There's two kinds of oscillators. First one, we're going to talk about some mass spring system. Now, I had set up something, and it was so confusing. It didn't help. It didn't help out at all. Maybe I can make. No, it's not going to make sense either way. The problem with this is you really need a decent spring in order to show a mass spring system, and I don't have any. And they tell me if I go to the school, I'll give Marvin a bunch of work to do. So we're not going to go to school. Instead, I'm going to have to do my best to explain this at some length. So a mass spring system is a system typically where either you have a wall. Remember, these little dashed lines mean it doesn't move. You have a spring set up like this. You attach it to the wall. You put a mass on it. You either push it in or pull it out, and it goes boing, 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 back and forth. Or you have it attached to the roof. You put a mass on it, and then you let it settle down, because when you first put it on there, the spring's going to stretch, right? So the spring stretches a little bit. And then you pull it down or push it up, and then watch it go back and forth. It's going to go up and down past this, what we're going to eventually call the equilibrium position. Why is it equilibrium? Because that's where the forces are zero, right? Net force is zero. If the net force is zero, then there are no forces there. We don't have to worry about doubt. And that's the definition. So that's the middle point of its oscillation. So it has no forces. So what's an oscillation? Oscillation means it goes back and forth the same amount of time. Usually the same amplitude. What the heck's amplitude? Amplitude is how far it goes back and forth. So if you pull it back 0.2 meters this way, you expect it to go 0.2 meters this way and then back all the way back to 2 meters this way. Now, in a perfect world, that's what would happen. And if there's friction, this actually doesn't happen. But it gets darn close. And for our purposes, we're just going to say it's the same thing. Okay? They ask you about friction. The answer to the question is it's going to be less. The amplitude is going to go down. They really can't ask you much about how much less it goes down, because the math gets really into the land of calculus very fast there. Okay, so simple harmonic motion is defined as any motion where the period is the same, where it's going back and forth in the same time over and over and over again. Okay, so if you remember correctly from your trig class, hopefully, if you see something that does this, it can be modeled as a sine or cosine wave. Okay? Now we're not going to spend much time on this model because it's not all that important for what we're doing, but we would spend more time if we're talking about waves. But the bottom line is this is the model, and it goes back and forth like this, back and forth. Theoretically, you learned that your that your equation was something like y equals the amplitude. This was how much it goes up or down, which in this case would be how much it goes up or down or left and right. Sine, probably a k, a theta, plus c, plus b. Now we're going to ignore this because that's just how high it starts, and you can add that in later if you're really excited about it. This is a phase shift, which means where do I start? Do I start by pulling down or pushing up? Don't really care about this. Now what's interesting here is period, if you remember correctly, period is equal to 2 pi over k. Now if you don't remember that, I'm not going to stay up late at night over this. I seriously doubt it'll be on your AP test this year. In fact, if it is, you better remember your trick. And there's not much physics to it at all. But what do want you remember, there is a 2 pi sitting here. The 2 pi is interesting because the 2 pi appears when I try to find my period formula. My period formula is going to be 2 pi square root of, it's going to be m over k. Now I need to explain this formula in a little more detail and spend a little more time explaining what a period is to begin with. Period is how long until it goes back to where it started. So if I start by pulling it here and let go of it, the period is how much time it takes to get back to the starting position. If I pull this thing down, period is how long it takes before it gets right back down to the same spot. It turns out for a massed spring system, in an ideal situation with a very good spring that does what it's supposed to do, unlike anything that I have in my house, the period would be, which is measured in seconds. The period is equal to 2 pi. And the reason why I mentioned all this nonsense is to remind you where the 2 pi comes from. Why is there 2 pi in this formula? Time it takes to go through a cycle, 2 pi. Well, 2 pi actually, if it's going through a cycle, it's going to be 2 pi there. Square root of, this is mass, and hopefully by now you know mass is measured in kilograms. And then spring constant, which is our friend newtons per meter. Now, why is it this way? Well, mass makes the period take longer. If this is a big old mass hanging on here, it takes a lot longer to get through its cycles. If you have a big spring constant, it goes through faster because the spring has more force per unit distance. Okay? So this is how you find the time. Okay? Also, you need to be aware what frequency is. And hopefully from last year in chemistry, you remember that frequency is equal to 1 over the period. Therefore, you just take the number you get from this, plunk it down here, and it's measured in oscillations per second, which is so brutal that somebody actually came up with a unit for it called a hertz. Okay, so these are the same thing, oscillations per second. Time it takes to get from a starting position back to its starting position, divided by the time it takes to do it. Okay. Right, that's oscillations. So beats per second. And by the way, this is seconds per beat, right? Period is how many seconds it takes to go through a cycle. Frequency is how many beats it goes through in a second. Okay? All right, more. We got a second. So that's our first version. Our second version of a simple harmonic motion comes from the simple pendulum. Okay, simple pendulum is something you should be familiar with. It's you take a string, you put a mass on the end of it, and you let it rock back and forth. Let it rock back and forth. So as a thing is rocking back and forth, okay, what happens, and as you should be well aware, the period is going to be the same. How do you know that? Because we built clocks out of it for approximately 300 years. Grandfather clocks have a pendulum that swings back and forth, and the time is always the same, even as it winds down to smaller distances. It still takes a second to travel its distance. And so the formula for a grandfather clock for the period shouldn't be shocking. It's 2 pi square root of that which makes it take longer, which is the length of the rod, divided by what is making it go. It turns out gravity's making it go. And so here's the formula for the period of a pendulum. All right, and so the period of pendulum is when it's going back and forth. That is the cycle by which we can say it's going back and forth and consistently. And we could draw, if we did a graph of its position versus time, it would do this, and we'd use the same sorts of formula. You could ask about the frequency of the period. You could do all those sorts of things. All right. So next question is intellectual, and that is, why is simple harmonic motion happening? What? Well, think about it. I just said it takes just as long to go through a little cycle on a pendulum as it does to go through a big cycle on a pendulum. That shouldn't be so. I'm going to explain to you, though, by looking at, let's say, a spring. I've got a mass. I've got a spring, and I got one of them. I'm using the same spring for both. One of them, I'm going to go big distances. And the other one, I'm only going to squish it a little ways before I let go of it. Okay? So if I squish it a little ways. So what happens here? Well, this is going to go a shorter distance, so you'd think it'd take less time, right? It's going to go from here to here, and then back to here, right? Same distance left and right, should be. This one's going to go much farther out there. So therefore, what's going on? But think about it. When the spring is squished this much, the force is kx, which means part of it's x. And this x is very different than this x here. So when it gets pushed all the way out to here, it's getting the force trying to get it to push the other way is going to be very much larger. Therefore, the acceleration is going to be larger. The acceleration is going to be larger. It's going to go much, much faster. And it turns out because it's proportional to the distance, the time is going to end up being the same. Okay? Same thing's happening with the pendulum. The pendulum, this component here is always going to be weight, which means this piece here is always proportional to the weight. If it's a littler distance, it's a littler force restoring it, so therefore it's going to have less acceleration. Even though it's going a shorter distance, the time is going to be the same. All right, so calculations. When you go to do a simple harmonic motion situation or an oscillating situation, the calculus for time is going to be one of these two formulas, right? One of the two period formulas. That's it. What else can you tell me? You can tell me how much time it takes to go from here and then all the way back, right? So it has to go all the way to there. That's the period. Well, you can also tell me, by the way, how long it takes to get to here, right? It'd just be half the period. You can also tell me how long it takes to get to the middle point, which would be a quarter period. After that, though, it doesn't work. Why? Because the acceleration is going to be bigger here, but my velocity is less, which means it's going to be faster here than here. If it's going faster here than here, the period cannot be the same for each little segment in between. All I can say is the time it takes to get to the back to the middle equilibrium position is 1/4. To get to the other side would be 1/2. To get all the way back to where it started is the period. And the period can be solved for by using this formula. Everything else would require using formulas from trig. I'm not going to have to use those, I imagine. More on why I say that, I imagine, in a little bit. Calculations-wise, the other thing you have to do for everything else is, what we're going to use is energy. We're not going to use force for much. Now, you could figure out acceleration at the two endpoints, right? Because you'd have the force there. You figure out the acceleration in the middle because there's no force at the equilibrium place because there's no force on it. Everything else should be discovered by energy, right? If I want to know velocities at some position, I'm going to do energy before equals energy after. Now, I have to explain all that, and I will. We'll do an example problem on the next video. Okay? All right. Whew. Last thing to learn in physics, at least until after the AP test. Here we go.